Hey, let's talk about protection, power system protection. So our semester has evolved, right? This is pretty much the last class with anything new from a materials perspective. And we want to kind of cap it as best as we can and talk a little bit about the evolution of the semester, right? The beginning of the semester, basic fundamentals. Then we moved into modeling of components that you will find on the power system that you may or may not have seen in previous classes. Then we actually started talking about analyzing power systems, and we did that with load flow. And we could do Newton-Raphson load flow. We could do contingency analysis. We could look at the operation. Is the system going to operate as expected? And then we started to talk a little bit about fault analysis, right? And all of those are really important, but in some ways, the fault analysis is the most challenging because it's the most unpredictable. You would never design a power system that you have all the faults occurring in one location. You design a power system so that you never have a fault, but that's not practical, right? These systems are designed to last for many, many, many years, 50, 100 years. And you cannot control all the variables that are going to reduce the likelihood of a fault. There are things you can do, but you can't do everything. And so every power system, no matter how small, even if it's in your car, right? If you look at your car and you look at a fuse box, there is built-in protection in there. Okay. Our power system, though, has to be a lot more sophisticated from its protection perspective because we want to make sure that we isolate faults. We would not like to trip unless we're certain that there's a fault or have a very high confidence that there is a fault. And we want to take the least amount of equipment out of service so that if the system has experienced a fault, we're not taking out entire towns, cities, that type of stuff. So last week there was a fault, I believe, someplace on campus that took out this building, right? I mean, on Tuesday, we had no power Tuesday morning, the day of the storm. So you can see how what a disservice it would be if you have this power system that a fault on campus would take out the entire power grid for the state of Maine. Right. So that would not be a good operating system, particularly on a cold day. And then the other problem is, where is the fault? Let's say the fault is in the basement of Barrow someplace, and you're in Portland trying to figure out what caused the entire power system to trip offline for the state of Maine. That would not be a good thing. Restoration would be very, very difficult in those circumstances. So limiting the amount of equipment that's taken out of service is essential, but you have to balance that with the fact that there isn't an infinite pot of money. Yes, you could make the most reliable system that minimizes the least amount of equipment taken out of service, but it would be at a huge expense. So we have a lot of balance and trade-offs that we have to do with power system design, and that also includes power system protection. So we need to think about that in all cases when we're designing, testing, and setting our power system, and then even restoration too, for that matter. The repair part of it is a lot of times is you just get the system back online, and then you have to do upgrades in the future. You plan that separately. It's very rare that a fault on a system is going to take out a piece of equipment for an extended period of time. That doesn't mean that never happens. You can have a fault inside of a transformer that causes some sort of serious fire, and maybe it's months or years for that transformer to be rebuilt or to buy a new one. So it can cause some issues there. And so some of the things that you do is you have redundancy in your power system, you have redundancy in your protection, but then you also have backups. And so if you're familiar at all with a distribution system in Maine or pretty much any place, if you have a failure out at a distribution substation, CMP, Versant, they have mobile subs that literally fit on the back of a semi. And usually they're open air. Sometimes they're enclosed, but you'll see sometimes down the road, although it's not that common that you'll see it, where you'll see a breaker and a transformer and some steel on the back of a flatbed. And so what they do is they roll it to the location that it's needed, they wire it up, and then they run temporary power through there. It might be a week, it might be a year. You don't necessarily know. So that capability is part of the power system protection. If we have a fault and we have a system that's taken out of service for an extended period of time, how can we get portions of the system up with a minimal amount of impact to our customers. So you build in some backup capability. So the power system, right, is take the faults out as quickly as possible. And you'll note that I put as quickly as possible, not ASAP, because you want to make sure that it's a fault. So removing faults, not tripping for high current conditions, but isolating faults. So you have to be fairly certain that your system is experiencing a fault. It's always better to err on the side of conservatism to say, go ahead and trip, right? If we think it's a fault, but sometimes that can be a bad thing too, right? Tripping the feed to a hospital might result in a lot of casualties if they don't have power for a period of time. So sometimes tripping can be a bad thing or a worse thing than isolating the faults. And we talked a little bit about that with battery systems in particular. Those tend to be ungrounded systems. And the reason why they're ungrounded is because if you have a fault on a battery, you can detect it, but it doesn't actually cause fault like heavy levels of current to flow. But there is a fault on the system, and you got to go fix it before that second equipment failure causes an actual serious amount of fault burn. So we want to do it as quickly as possible, and then limiting what is taken out of service. The healthy stuff should stay in. You can't have all the healthy stuff stay in, but it can happen. So what happens during a fault? Lightning, it could be an animal, a tree, equipment failure, whatever. You experience a fairly significant increase in current. And then the result is that the entire system responds because electrons are perfectly fine to flow through a lower impedance device. They don't care if it's a fault. They just want to go back to where they came. They're looking to get back home. So they will impact currents everywhere in the system, and voltages will also be impacted. And as our voltages start to degrade, it actually can make protection much more difficult. If you take the follow-on class of this one, we actually talk about polarizing voltages and how you can actually polarize with negative sequence components to actually get pretty good results, whereas the zero sequence or the positive sequence might not be enough to be certain that you actually have a problem. We can't measure 55,000 amps directly because you would need massive wires and you'd have to run that all over the place. So we run transducers, right? Instrument transformers. Current transformers take the 55,000 amps and convert it down to 20 amps. Still a lot of current from a perspective of what it normally sees, but 20 amps, I can get a number 12 wire to handle 20 amps and it's not going to cause any issues. So your transducers are converting those crazy high quantities into much more manageable values. We have it for current and for voltage. Far more current transducers or instrument transformers that are current transformer than potential transformers because far more of our protection is based on what's going on with the current. That doesn't mean you don't use PTs to get the voltage input, but CTs are far more common. Every system that you'll see will have a CT, and it may or may not have a PT. It just depends on what's going on. And part of the other reason too is the location of current transformers. They're really easy. You put them on bushings of devices. You put them on transformer bushings, breaker bushings, reactor bushings on loads. It's really easy to mount them. Where PTs, you normally have to build a separate structure to actually install the PT. So it's way less to have PTs and CTs, yes.
Are PTs and BTs the same thing?
Yes. You normally see potential transformers as the more common one, but you'll see voltage transformers used. Sometimes you'll actually see CCVTs, capacitively coupled voltage transformer, which is a potential transformer is an actual transformer, right? It has windings, primary and secondary, and steps the voltage down to a more manageable level. Capacitively coupled voltage transformer is a voltage divider network. You take two capacitors and you just set up the voltage so that 98% of the voltage is divided across one capacitor, and the other one is divided across the other. So once you start getting into higher voltage, CCVTs are a lot cheaper to go with. But you can have fuses or you can have a simple overcurrent device. So fuses are the cheapest way to go because the protection is built in. You don't even have an instrument transformer. You just have a device that heats up some metal or mixes of metals inside of, a shell, essentially, a cylinder, and you can go ahead and isolate there. Fuses are no longer allowed in your house, right? So if you have a fuse box in your house, you wouldn't be able to get insurance, even though fuses are really super reliable. It's just that people would defeat it. If you keep plugging in your toaster oven and it trips the fuse, burns the fuse, what do? Let me go look for pennies in my drawer and see if I can put that in there, because the penny can conduct current. Well, the old copper ones, not the new ones. But the old ones could conduct current. And so people would say, this is annoying. I'm paying $1 for a fuse. So let's just increase the current capability of the circuit, put a penny in there. And because they thought, oh, we're just pulling more current. But the problem is that the toaster was not operating properly. And so they had lots and lots of fires. And so the way that the National Electric Code folks said is, let's just go ahead and no longer allow fuses for protection at people's homes, and let's have circuit breakers. Those are much harder to replace. Once a breaker trips, then it usually fails open. I have some breakers just recently where the backs of the breakers, where they plug into the bus bars, they actually will melt there. So you can actually have some faulted ones there. So it's not obvious what the problem is, but generally speaking, breakers will fail. They'll fail in the open position. Fuses are still used extensively in industry. Like if you look at a motor controller, you find fuses there pretty commonly, although they're now switching to a resettable solid state fuse. And then again, out on the distribution system, you see fuses. Anytime you see one of those trash can transformers on a pole, those are almost always protected by a single phase fuse. Okay. If it burns out, no problem. You might lose 2 or 3 customers, but it's not the end of the world. So fuses are still the most commonly protected device that you would see to use for overcurrent. Anybody here drive a newer car? Take a look at the newer. Oh, how about in the last 8 years? You got me beat. I've got a 13-year-old car, but fuses, if you ever looked in the fuse box, there's probably 50 fuses in there. So on automotive applications, you see fuses everywhere. If you have a dishwasher, you usually will have a fuse inside to protect the device. And so sometimes you wonder why your dishwasher doesn't turn on. It's because the fuse popped. So still very, very common to find fuses. But we want to use more sophisticated. Yes, sir. Well, you can use resettable. So you don't see a lot of resettable fuses. If they're solid state, you see them. Most fuses are when they melt, that's it. You got to replace them. There are some, but they're not as common. And you can use breakers, but it's a cost thing. If I have to put a breaker with the intelligence to be able to detect a fault and trip, that's probably 2 to 3 orders of magnitude more expensive than a fuse. So I can buy an underoil fuse for $18 at, a local, like Gilman Electric, essentially. Whereas to go buy a breaker and the relay that, or the controls for it, even if it's built into the breaker, sometimes they have little trip units in the breaker that are adjustable. That's tens of thousands of dollars to be able to do that. So it's just cost. That's all it is. Cost questions. But the relays will sit there, and even those trip units in some of the electronic breakers, well, they have electronic smarts for the breaker. They actually will take the currents and voltages, always the current, sometimes the voltages, and then they will make a determination whether a fault is occurring. You, as the settings engineer, figure out how to configure the relay, not like the base configuration, how many inputs, how many outputs, but more like, hey, I need to have a pickup setting of 2 amps and a time dial of 3 to go ahead and provide adequate protection for my system. So the relays have a lot more control and sophistication, but it's just more complexity to it. So if you relay detects that there's a fault, or it's a fault that you called it, then it issues an open the circuit command. That could be a breaker. It could possibly be a starter, could be a recloser, a circuit switcher. There's all different types of device, and they each have pluses and minuses to them. But generally, if you're experiencing a fault, you want to open a circuit breaker because it's capable of interrupting. Remember, we have 2 currents, right? We have the symmetrical value and the asymmetrical value. So there's a lot of current and it's got the ability to interrupt that major amount of fault current. Now, when I talk about primary and backup, I am usually not talking about redundant. Redundant usually means two completely independent devices at the same location that essentially provide the same protection. And so the higher the voltage you go, the more important the systems are. Those usually are going to be equipped with redundant protection. And in some cases, it's required. There's a requirement by NERC called BPS, Bulk Power Systems Requirements, which mandates you actually have to have two separate protection channels or trains, depending what you want to call it. And in some cases, you need to have separate batteries, separate DC batteries, separate physical separation between the two. So if a fire or if somebody runs a truck into one portion of your control house, it doesn't limit the other one from operating. So it's getting more and more in terms of having, better capability to, if something worst case happens in one part of the building, you can still take the system and isolate it. It's almost becoming like a nuclear power condition where you have a lot of safety built into it. What I'm talking about here is primary and backup. Primary is the closest to where the fault is occurring. The backup is usually remote. Okay. So a primary backup, which would be an example, would be a distribution line has, I don't know, a bunch of reclosers on it, and there's a fault that occurs on campus. And so the recloser closest to campus or the breaker closest to campus should issue a command to go ahead and isolate. But upstream of there's a breaker at the substation that sees that there's a fault on the system. And so the reason why it's backup is because it sees there's a fault, but waits. I'm waiting for the primary protection to trip. So I'm delaying my trip command a certain amount of time. That's called coordinating time interval. I'm waiting that coordinating time interval, or CTI, to give the primary protection the opportunity to trip. If it doesn't trip within my allowable time, then I will go ahead and trip as well. So that's the backup. And you always prefer primary protection to operate and not backup because primary is closest. So you're going to limit the amount of equipment taken out of service, which means you got happier customers because you're not taking out the town of Orono, you're taking out campus. And it's much easier to troubleshoot. If the primary protection says, hey, I tripped, anything downstream of that is the culprit. But if the backup protection trips, and anything downstream of that, which is usually a much bigger area, will go ahead and cause a trip. So you always have to have redundancy. Your house has redundancy too. May not be very good, but everybody's house here has a 20 amp or 15 amp circuit breaker for the circuit that feeds your toaster oven. But there's also a main breaker too, right? 100 amp main, 200 amp main. And if that fails, this is a worst case, but out on the transformer, on the high side of the transformer, the utility has a fuse that if that current continues to stay high, it will go ahead and take that out of service. And even from there, back further along, there's a recloser that's saying, hey, let's go ahead and isolate if the current gets too high. And then you go to the distribution substation, and then you go to the transmission. So there are multiple backups. The problem, though, is the further away you get from the fault, I'm going to use a term or a phrasing that might make a lot of sense. It's harder to see be able to see from the device. So the example is, if I'm looking over here and I can see out the hall, then I can see what's happening over there. But I can clearly see something that's a lot closer to me. I can figure out what's going on. So the further you are away, the harder it is for the relay to see it. And what I mean by see it is to see that it's actually a fault. Because a fault that happens way out away from me might look as a lot of current for the primary device, but it might be almost noise for the backup device. And so the further and further you get away, the harder it is for those backup devices to detect it. So we have a bunch of different systems that are specified, and I say there are two main systems, but I added a third bullet because that's not really a system, that's a modification. So the first two is radial. Radial is when everything is going out from a center point. So you radially extend out from a center point. That's your distribution system. You have a substation, power radiates away from the center and it goes to the load. That's the easiest to protect by far, because usually power is in one direction. Once you get to the transmission level, the power system is all it's not radio, it's network now. And power can go in all different directions. And it might go in all different directions. Sometimes it's a preferred, like power goes generally from New Brunswick to the rest of New England. But electrically speaking, there's nothing wrong with power going from New England into New Brunswick. Say Point Lepreau, which is a nuclear plant in New Brunswick, trips for whatever reason under really cold conditions. They need a lot of power. Power can go to New Brunswick and the system still can handle it, no problem. This DER, which you're starting to hear is distributed energy resources. It used to be called distributed generation, but now it's called distributed energy, and mainly because of battery systems, because those aren't necessarily generators, are they? Sometimes they're a load and sometimes they're a source. So you can't call it DG, so we call it DER. And DER now has made it way more complicated for distribution systems because they're still radio, but now my power is bidirectional. If I've got a 5 megawatt solar farm that's on the end of a distribution circuit, the power is going to be going back into the grid. So now it used to be any power that would go to one direction is okay. So you can run massive current in one direction, and that's load. Any power that would go back would mean that there's some sort of a problem behind me, so go ahead and trip. Now with distributed generation, we're getting lots and lots of energy going back, so that assuming of direction and using that as a settings value, because it's easy enough to go ahead and determine the direction of power. Is it in this direction or this direction? As long as you add the voltage part, now we can't use that to the same level anymore. It's a lot more complicated. So here's a radial system, and I'm not going to worry too much about DER. But here's a system that I need to design, and I've got two options. I have the top version and the bottom version. Which is the better? If you read it, it says the bottom scheme is preferred. Why is it preferred? They both have 3 breakers. They both have 3 buses. They both have 3 loads and 1 generator. Why is the bottom preferred over the top? Well, think about a fault on bus 3 or below. In either system, it's isolating only the load associated with bus 3, right? So there's no advantage to that. How about if a fault occurs between bus 2 and bus 3? In the top system, the only way I can isolate that fault is I have to take out both bus 2 and bus 3. In the bottom system, I only have to take out bus 3 and the line going to it. So I have less loss of less customers just by changing the location of a breaker. I still have 3 breakers, but I provide a little bit better limit in terms of my customers. There is a downside to the bottom one, because if the breaker that's located at bus 2 trips, look at how much territory I have to do to search to find where that fault is. I have to include the line between bus 2 and 3 and all of bus 3 and all their loads. All that location has to be detected. Whereas in the top one, if the breaker at bus 3 trips, then I know that's where I have to focus on. If the breaker at bus 2 trips, but not at bus 3, then I only need to focus at bus 2 and the line between them. So I'm shrinking the amount of area that I have to detect. So there are trade-offs, right? And usually less loss of customers is preferred, usually. Because again, if you're not connected with your customers, you're not making any money. So what the hope is that you have enough sophistication in your relaying that you can actually use it to detect approximately where the fault is. And you can do that. You can use relays to have a feature called fault location, which if you tell the length of the line and the impedance, the nominal impedance of the line, you can predict within 10% or so where the actual fault is located. So we would pick number 2 instead of number 1, or the bottom instead of the top. The other advantage too is that this system over here is really simple. It's just a bus. So that's a real basic system. Over here, there's no advantage to having a breaker on the high side or the incoming side of the outgoing. And over here, I just have to add one additional bay position in my distribution circuit. So I've already got a fancier substation because I need one breaker there. So there's not a huge cost differential between bus 1 and either configuration. So the second one tends to be a little bit cheaper to implement than the first one. Oops. So your fault current in all cases, right, is V divided by Z, or the voltage divided by the ohms. And if your ohms go really, really low, then your current goes really, really high. And so the further the fault is from your source or your relay, the lower the current's going to be. So remember we talked about seeing the fault? Another term for that is called reach. How far can that relay reach? Can it touch out on the system before it no longer can reach and detect faults in that specific location? So the impedance of your system can have a pretty big impact on what's going on. And so one of the things you need to think about is, I can size a wire in my house a number 14 or a number 12. Well, you can't really do that the same in utility circuits because sometimes your cables have to be capable enough based on the amount of fault current that they're going to see. So you might actually have to go with bigger cable sizes than you anticipate. That's why you don't buy, medium voltage cable with an insulator that's less than like a 4-aught or 2-aught cable. You don't get number 12, 5,000 kV insulated cable. It just doesn't make sense. It's just too much fault current. Running 2,000, 3,000 amps through a number 12, it vaporizes instantly. It basically acts like a fuse. It found the fault. Yeah, you know exactly where the fault is, but now you got to spend a month or two, right, replacing that burned up cable. So generally, you don't want cable failure. You try to limit that as much as you can. So what we do, because the further away the fault is, which means it might have some primary protection closer, then let the primary device take care of it, not me sitting here. And so I'm going to use a relay, which is called an inverse time characteristic. When I say inverse time, what does that mean? You take the negative of time, you put 1 over time.
That would be a free. But that doesn't seem like you're talking about in the other direction.
Right.
Go into a time before the current one.
Well, it's not looking back in time. It's just like when I think of an inverse time characteristic, what does that mean? You have to use narrative discussion for it. Inverse time means the higher the current, the lower the time. So they're the inverse of each other, right? Higher I means a shorter current, a shorter time. And then the opposite, lower current means a higher time. And so almost all your relay schemes will use an inverse time characteristic to go ahead and do that. You do have some that are called definite time, which is if it's above a value, trip if it's there for more than 0.2 seconds. But most of your applications are going to use inverse time. They're easier to coordinate typically too. And then we talked about those coordinating time intervals, making sure your primary device trips before your backup device. That's called coordination. So you have to make sure when you're looking at your system and you're setting these relays, is the one that's closest to it, is it given sufficient time? So you can have longer delays, or you can have higher pickup values to go ahead and do that. And the reason why the higher pickup values goes back to the first paragraph. The further down the distribution circuit, or any circuit for that matter, it is, the lower the current's going to be because you have a higher impedance there. The higher or closer you are to the source, the higher the current. So I expect that I'm going to have higher current values closer to the source because I've got all these loads. So I don't need as sensitive a pickup as I do, way down feeling Jim Bob's farm, essentially like that, where I need hardly any load to support. And then this is just a standard, and actually it's a pretty consistent standard. if you're a distribution system, you'll have 10,000 amps or less of available fault current. And that's because distribution devices are made to have less than 10,000 amps. If you look at the circuit breakers in your house, you'll see a 20 amp, 15 amp continuous current rating, but they also use a value of 10,000 amps. So if there's a fault, that breaker can interrupt up to 10,000 amps of current. And I've actually seen this. I've actually seen line reactors out on the system. This is many years ago, but at Harvard Power System in Cambridge, they actually had series reactor because Boston Edison, that was the name of it at the time. They actually had way too much fault current for what Harvard Power System can handle. So they actually had to knock down the available fault current just by putting impedances. And they use reactors because they don't consume real power, right? They might affect the power factor, but they won't consume watts or joules, I should say. So you don't have to pay the price for that. And series reactors are used, not the most common, but you do see them out there if you have too much current. Here's the inverse characteristic, and you can see this is current and time, right? The larger the current, the less the time. And this is the no trip region. So below and to the left of the curve. So here and here is the no trip. The trip region is above and to the right of the curve. So if you're trying to envision how these devices are in fact working, that's what they do. And with relays, you can get a perfectly straight line because it's just an equation in a computer. It's literally just based on, what somebody came up to model this particular equation. And you can change the level of inverseness, if you will, by just picking a different curve type. You've got inverse, very inverse, and extremely inverse. As you go from inverse to extremely inverse, what you see is a much bigger inverse time characteristic. So you see the extremely inverse, as I get more current, I get way less time, right? Or I need way more. So way more current means way less time. Way less current means way more time. The most common one you'll see, or at least I've seen, is what we call a Schweitzer U3 curve or a very inverse curve. There are 5 standard ones for inverse time characteristics that you'll see, but the most common by far is the very inverse. You do use the other ones a little bit, but way more to see the U3. So we already talked a little bit about backup protection. So great for doing backup protection and also providing reasonably good protection for your power system, although that might be a drag if you're, got some high impedance fault at your house and it doesn't look like a hard fault because it's not, and you're just feeding arcing energy into your house and causing more and more damage. So that might not be an ideal thing, but it does do a pretty good job of allowing that primary protection to go ahead and trip. So that next bullet, which talks about minimum pickup current, and the minimum pickup current is actually a misnomer because most relays, when you have a minimum pickup, they actually don't even pick up at your minimum pickup. They usually pick up at like 125% of minimum pickup. But you've got to make sure your minimum pickup is below any somewhat realistic value of load current. Okay. What that means is if you have a load of 15 amps, you should never have your tripping devices trip below 125% of 15 amps because your device, whatever you're setting up as, might have a mechanical overload. A mechanical overload is not a fault, is it? A fault is I've got current going someplace it shouldn't. But if I've got a mechanical system with a lot of load on the shaft and it's being driven too hard, that's pulling in more current than what that system is designed for, but that's not the relay's problem. The relay is said, that's not my problem. You, the mechanical people, have to figure out a way to ensure that that doesn't happen. There are some things you can do with electrical protection to go ahead and provide that, but it's generally not part of fault protection. So when you talk about motors that are in industrial applications, you have protective devices that are specific for motor protection. And what would be one way to identify if a motor is running too hard? Maybe, but usually if it's vibration, it's a bad bearing.
That isn't current thought, that doesn't.
Its current is high, but that's not the real
Temperature.
job to say, hey, the current is high. What would you do if you were designing a motor protection scheme to provide protection of that motor if it's overloaded? You can look at the current, but remember the current isn't always the best indicator. And again, the current is looking for fault. What would be one of the best ones you could do?
But I think torque, but I thought that's just what the current was indicating.
Sometimes it's hard for torque.
Heat.
Yeah, heat. If something's getting hot and it's hotter than it should be, then it's probably running too much current through it, too much load, so trip it. So a lot of motor protection, if they're somewhat important motors, they actually have these devices called RTDs embedded inside the insulation, and their whole job is to monitor different spots in the motor. And if it gets above a certain temperature, you're going to damage the winding, the insulation, go ahead and trip it. There are protective skis for torque and measuring all that stuff, but usually the mechanical folks just say, that's your problem. You know, if it's under overload conditions, we'll take care of it in the motor protection system and do that. But you could also say, like, there are applications that who cares? If the motor dies, well, you know, we'll just replace the motor. But if it's a motor that has a 6-month lead time and costs you $80,000, you might want to protect the motor so that it doesn't burn up. So there's just, again, the higher, you know, if you're willing to put protection in, if you want to protect a $500 motor with a $10,000 setup, go for it. Somebody will design a system for that, but it just becomes impractical, so people don't do that. Let's see. And so our pickup is important for fault. And then the other thing too is when you have a feeder that's outaged for a while, usually it's greater than 30 minutes, there's something that called cold load pickup. You're in your house and you've lost power for 4 hours. It's chilled out in your house. Your refrigerator is getting to be whatever the room temperature is. Your well pump, you know, you forgot you flushed the toilet. Now you need to run your well pump. And your dryer was running before the power went out. And you had your just a bunch of different things. All of a sudden the power comes back on, and everybody who was in your case that had no power, their entire system turns on just like yours did. And so under cold load conditions, again, outages for greater than 30 minutes, you can have massive amounts of power demand, way more than what it would be under normal full load conditions, even above the 125%. So one of the things you need to do is include higher pickup settings. Again, as long as you don't damage the equipment, your pickup settings will temporarily be higher until things stabilize. How can you tell things have stabilized? You give it 5 minutes, check your watch. Oh, it's been 5 minutes. Things have stabilized by now. Does that seem reasonable? One person says no. What if you'd had lost power for 7 days versus 30 minutes? Wouldn't the people who've been out of power for 7 days have a lot more demand for a lot longer period of time? And so the best way to check if you've returned to normal is, did the current going to the load dropped back below what we would expect for normal full load and stayed there for a period of 3 to 5 minutes? So you're riding like this really high, and then at some point people's houses warm up and their refrigerators are down to temperature, and now people start clicking their loads on and off, and you start trending down. Once you stay below that normal full load condition, then you readjust your settings to be the normal pickup values. That's a very common, you know, cold load pickup condition. I've actually set it. Works really well. I included this in there because our friends at Schweitzer have done an amazing job of making really good products, but even better documentation. And these are a set of curves. It's actually only one characteristic. If you look at the curve description on the right, you see it says U3, very inverse curve. These are very inverse curves. Why are there so many of them? What are there, 10 or so? Because of this multiplier right here. I can either multiply by 0.5, so make it faster than normal, 1, 2, all the way up to 15. So I can increase or decrease the speed just by changing the time dial. Time dial is an old expression. Old electrical mechanical relays actually had a dial on the top, and you would rotate it, and that's why they called it the time dial. Now it should be just called multiples of time, which would be a better description. Can I move the curve this way? Left or right? The answer is no. Because if you look over here, that's multiples of pickup. So if you set your pickup to 3 amps secondary, then you're just going to plug in a ratio. So you're going to get the actual current divided by your actual pickup, and that's where you get multiples of pickup. So you can't move left or right because it's a unitless quantity, right? It's basically per unit. And so the only thing you can do to these curves is move them to the left or the right when you're plotting against multiples of pickup. If you were plotting in amps, then it does move left or right. But it's not really plotting, or doing the calculation here, because if you notice what M is equal to the actual current divided by the pickup current. So it's just a ratio. And remember how I said it's an equation? This is the equation Schweitzer uses to figure out those times based on the current or the multiples of pickup. So your independent variable, in this case, would be current, and your dependent variable is time. So time versus current curves should be, this is my y-axis, and this is my x-axis. You sometimes see them flip-flop, but it actually isn't that case. Time is not the independent variable there. This is actually the dependent variable. So it's a little bit confusing, right? If you look at all your previous engineering study classes, x-axis is almost always time, right? This is the opposite. This is my current is what dictates how long the time it's going to take. So we can use inverse time characteristics for network systems, but it's not as effective because directionality can be used, can really challenge things. So what we start to do is we look at directions, because now we have to determine where's the primary and where's the backup. So now we need to look in the forward direction to say, if there's a fault behind me, I'm generally going to ignore it because that's somebody else's responsibility. That's called somebody else's zone. So when I'm protecting on a network system, because directions can go in all different ways, I have to add more protection devices, but now I have to start looking at direction, because I don't want a breaker that's protecting a line going from left to right to trip for a fault on a line that goes from left to right in the opposite direction. What I'm saying is, if I have a device here, I want this device to protect for faults that way. I'm going to put another device to protect for faults in this direction. And this is the worst. If you have this breaker here that trips because of a fault over there, you've really made it difficult to go and provide an opportunity for your line folks to go ahead and find where the fault is. This is a much, much harder case to crack. So directionality is where you really got to have some challenges there. So the cheapest is directional overcurrent with, go ahead. No, no, because usually when I do what's called coordination, I'll have my primary curve will be here, and my backup will be over here. And what I do is I compare a time at a certain current, and I'll see do I have 250 milliseconds or 350 milliseconds of coordinating time interval to allow that primary device to trip before the secondary device? And then if not, I will move this curve up a little bit to get more coordination. And so then I'll just slide it up a little. Even old-fashioned relays. Yep. Old-fashioned, the inverse time characteristics, I learned pretty quickly. It doesn't make sense to have a static relay that you can't adjust. So they actually had they had variable values of pickup and variable values for time. And like I said, that's why they use the term pickup, because literally the relay wouldn't start to rotate until it actually reached a threshold or pickup value. And then the same thing, you had a time dial, and the old school time dials, all they used to do, it was amazing to see how they build these devices. So it was a shaft, and you had a set of contacts on it. And the shaft would rotate, getting the contacts closer and closer and closer to coming into contact and closing in trip. So how do you make it have a longer time? You literally rotated the shaft further away. And they have numbers on it to say this is 1, 2, 3. So they were like super duper calibrated devices because it was all analog, all mechanical systems. But that was a dial because they would rotate the entire shaft. If you find old, what we call them electromechanical relays, they're not all being replaced, but almost all have been replaced. It just, they're harder to maintain. You can't get spare parts. Solid state or microprocessor based relays have been around for 30 plus years. And even then they had solid state relays. So they would use, power electronic devices to do it. But yeah, I don't even know if you can buy EM relays anymore off the shelf. You basically have an A to D converter, and then you just run it through a computer, and then it makes a determination of trip or not. So the newer relays are much cheaper even than what the old ones are. You can buy a high quality Schweitzer relay, a 700 series basic relay for $800. They're called the SEL 501. It's 2 channels, program easy. You've got fault monitoring. It's just so much cheaper. So I don't even think you can buy, unless you're buying like spare parts for an application. And I only know this because I've worked on nuclear plants in the past, and nuclear people hate change. Something's been in service for 60 years. It hasn't given us any problem. Why replace it with newfangled stuff? Let's keep working hard for that old-fashioned stuff. So they'll have gone out and they'll get, spare parts for these 60, 70, 80-year-old relays, and they'll keep maintaining them and keep cleaning them up and fixing them, and they just last forever. Microprocessor-based relays wouldn't last that long, but, all the other features, they do it. So it depends. Like the New England nuclear plants are really hesitant for change, but I know Dominion in Virginia, they're much more. They were just replaced all their generator protective relays with Schweitzer 700G relays. They didn't have any issues with it. Well, they had a lot of issues, not with the relay replacement, but figuring out how to set them, because again, they were used to doing old-fashioned way, had no idea how to set them, but they had other issues, like knowledge issues, basically. So this here has been the most common, are differential impedance, which if you're just not directional impedance, which you're just looking at the impedance, a line should have a certain amount of impedance. If the line impedance is less, as calculated by V divided by I, then you've got a fault. Go ahead and trip. So most of the time you see impedance relays, distance relays, work really, really well on the power system. A lot more have been moving to differential, and that's all because of computers. So we can have a 70-mile, 100-mile long line where it was impossible to compare basically KCL, current in equals current out, right? But if you're 100 miles away, it's hard to run a 5 amp CT signal, a current, from one point to another, which just wasn't practical. But if you take and put relays, they're called 87L relays, on each end of the line, have them communicate over fiber, they can actually coordinate their times and check to see, yeah, these are good or not. So some of the newer protection is switching to differential. Just more cost effective, more reliable. Your zone is very defined. But even in the differential schemes, they have backups, and backups usually translate to directional impedance, because the nice thing about an impedance relay is it doesn't need any communications to trip. as part of it, what's called a step distance scheme. It's just looking at impedances. If it's within this one, trip quickly. If it's not in this one, but the next one, then delay it 20 cycles and on and on and on, up until you can even get to 5 zones. So step distance relays don't need any communications, but differential protection needs communication, especially if you're talking greater distances. Oh. So directional relays, these are the ones that protect high voltage transmission lines. You see them everywhere. Super duper common. You use your instrument transformers to detect currents, not only the magnitude, but also the angle. Really, you're detecting the direction. And you compare those, and then you figure out, is the fault in the forward direction or the reverse direction? And so the relays will communicate to each other. I have fault current going towards you. Is that what you see? And then the relay at the other end of the line says, nope. So an example would be like this. Let's go ahead and show. Here's a line protected by 2 breakers on the line. If the fault is over here, this relay says, yes, I've got a direction that's going forward. So I'm ready to trip if you're okay with it. But this relay over here says, no, I see it in the reverse direction because both of these are looking towards each other. So if the fault is behind it, this actually will transmit a block signal to say, you know what? That fault is behind me. So don't trip. Don't trip quickly. So when you use directional, you can speed things up. This one over here only has to wait 1 or 2 cycles before it says trip. Because by the time I've waited 1 or 2 cycles, I had better have received a signal from the other terminal or the other relay to say, yes, it's in the forward direction. Or no, it's not in the forward direction, block you. But the other thing too is I'm going to wait 1 to 2 cycles. But what if the fault over here is not taken out by this breaker? What if it failed? Then this relay can back up as long as it waits long enough. So if I wait 20 cycles, hey, I waited 1 or 2 cycles for a very fast trip, but you told me to wait. You were blocking me. After 20 cycles, I still see a fault in that direction. I'm ignoring your block. I'm going to go ahead and trip. And that's how that protection provides backup protections for faults down the system. So you can use high-speed communications and you can still ignore them depending on how long the fault is allowed to persist. Works really, really well. Used to be that you used to use power line carrier, right? We have a wonderful transmission line, not for power, but we have an aluminum conductor that we can transmit medium frequency. You all are EMAGS experts. What's 30 kilohertz to 300 kilohertz? Is that medium frequency stuff or is that low frequency? When I think of low frequency, I think of audible. Is that medium or is that considered high? I don't know. But that's medium frequency stuff. So I'll just run on top of the 60 hertz, I'll run a 30 to 300 hertz signal that basically I transmit at a different frequency. So let's say if I transmit at 195 kilohertz, that's a normal, everything is good. If I move it to 200, then I'm saying block. So you would just run a Fourier series on the system and determine where's the power. Is it at 195 or is it at 200? And so it used to be that you'd actually use the transmission lines to actually provide the protection for your system. Now that's becoming less and less because there's so much automation at substations. You're almost always running fiber between the 2 substations and you're communicating that way. So instead of having power line carrier, which is what that's called, it typically will be used, it'll just be over fiber. You see this in Maine a little bit more. You'd see microwave, like what TV, like NPBN, what they transmit. They would just use microwave towers. So you'd have towers and they would communicate over microwave. The problem with microwave is it's line of sight. So you got to make sure that there's no trees in the way, there's no buildings in the way. Otherwise you can get it. But not that much anymore because again, you get fiber optic, it's so cheap to run. You can use radio, but you have limited distances. And the other problem with microwave and radio is it's much easier to hack. So if you're a bad guy and you want to cause a trip at a plant, you start interfering with the communications and then it no longer operates the same way. So hardwire is usually best. That's why you have to be concerned about security when you're just using wireless. With power line carrier, you're running that 30 kilohertz to 300 kilohertz signal down the line. But you've got to be careful because that signal can go all throughout the power system as far as the power will go. So it could block other relays that you don't want it to block. And so what you do is you put at the end of the line, you see that something that looks like a trash can almost. That's called a line trap. You know what another way to call a line trap is? It's just an inductor. It's a series inductor, doesn't consume any power, but it blocks the high frequency stuff from continuing on. So this is really good for high frequency, or higher frequency, 30 to 300, but it doesn't block any of the 60 hertz stuff that we're sending down the line. Normally you see it on phase B. That's what I've seen, but you can put it on any phase. Here's the concept of an impedance relay or a distance relay. Again, you have a line that's connected by two breakers with relays at the end of the line. And I have a fault to ground someplace on the line. I have no idea what it is, but it's someplace out on the line. And so the normal line impedance, right? This line, we're going to do a short line equivalent. And we're going to say it has a value of Z there. So normally when I divide V divided by I1, I2, you get at least the Z actual is going to be greater than Z line, right? Should be at least greater, especially when you add the load. But if the fault is out on the line, now it just becomes a ratio of the actual line impedance. And so do you remember how I said I could use fault location? So if I have 80 miles in length and this one is 60 miles and this is 20 miles, then I can go about 60 divided by 80, depending on, or 20 divided by 80. I can tell you approximately where that fault location is just by looking at the impedance. I'm going to back calculate this value of X based on the V and the I, and then compare that to the line impedance and say it's 20 miles out on the line or 60 miles out on the line. So again, really helpful because if you had to walk the entire length of an 80-mile line, it used to take you days to do it, right? You'd have to get out on a four-wheeler or pick up a four-wheel drive truck and then just drive the entire length of the line. Now it's all done, they fly over with drones. But you don't even need to fly over that hard. You just know, hey, the fault is around 20 miles out. So they'll send somebody out in a truck with a drone, and then they'll just survey starting at 20 miles and they'll go in one direction and in the other direction, and then find the tree or whatever that may have caused the fault to happen there. How do you set line relays? Well, typically you have 3 zones. This is for what we call a step distance scheme. So the zones are based on the level of time that they trip. So a zone 1 relay, there's no delay. It trips instantaneously. And that's typically set for around 80% of the line impedance. The reason why 80%, it's less than 100%, and it's not 92 or 97%, because again, I have a model of my transmission. That's not exact. And the impedance of that might be, a tree or something that has included in there. So I'm darn sure that the fault is in my zone. It's on that line, and I'm tripping it at 80%. So I don't go to 100% because I have some unknowns and I might overreach the zone that I'm responsible for tripping, and that's bad. So there's no wait, there's no delay, trip. A zone 2 is set at least the length of the line plus some margin, 120, 125%. And again, that one is guaranteed to cover the entire length of the line plus some. But because of the plus some part, I'm reaching into somebody else's zone, which means I could trip my relay or my system before the remote device, that's really the primary protection for it, that actually issues a trip command. So I don't want to trip unless there's a problem on that second line. So I'm reaching 125%, but I'm going to delay it 20 cycles, let's say, a third of a second, to allow the adjacent line to clear. And then my zone 3 is, all right, well, the fault is definitely outside the zone. And the breaker at the remote terminal failed to open for a fault that it's responsible for protecting. So I have to set my protection to provide some backup at least as long as the farthest line in the forward direction. And so your zone 3s get you in a lot of trouble because NERC has mandates about you should not trip within a certain time for faults that are pretty far out on the system because it could look like really heavy load. Those zone 3 settings tend to be so low, sometimes it's actually looking like load or possibly looking like load. So some of the time you actually have to block a zone 3 on what's with something that's called load encroachment because load or heavy loading or faults can look the same. But the difference is heavy loading usually has a lot of resistance and very little inductance, where if it's a fault, it tends to look like heavy inductance and very little resistance. So if we compare the power factors, right? The power factor for a line is a load would be between plus or minus 0.9. But if it's a fault, it might be 0.2, 0.1. So you only would block operation, in that limited range of power factor. Okay. And then you get impaired impedances. And so your protection for a 3-phase fault doesn't always work the same for a line-to-line fault. So that becomes problematic, and that's when you use other schemes to protect it. Here is something that caused a lot of problem in industry. And anybody alive in this class in 2003, other than me? Say still a few people, right? Were born 2003, August 14th. 3 days. Maybe you were the harbinger, right, of the problem. So, but most people have no idea what happened on that day. But 26 states and parts of Canada lost power for a fault someplace in Ohio. Remember how we talked about limiting the loss of load? You think that was limiting loss of load when half the continental US and parts of Canada lost power?
Not the whole US.
Not the whole. Not a good thing. This caused a lot of problems. And NERC got really involved, and now this should not happen again. And the reason being is because a relay setting was here, right? No, sorry, a relay setting was this line here. This was just inside. So when your impedance is less than the actual impedance you calculate is less than your setting, you trip. Over here, it's no trip. So you can see under normal operation, it was over here. But during super heavily loaded condition, it actually moved inside that zone and caused a trip. So it shouldn't have been set that sensitively. And as a result, 26 states, a lot of really upset people. Federal government got involved. I don't know if fines got issued, but it was years. It's still some of the residual stuff is happening. But that was a 345 kV line in Ohio tripped and quashed a lot of dreams. But it was a big deal. Not as big a deal to the public. If you were living in New York, you just walked across the Brooklyn Bridge to get home to New Jersey. I mean, it was, there was no transportation because all the electricity in New York City was shut down. So getting in and out of New York City wasn't easy. So people had to walk. Fortunately, it was a nice day, but you had to walk everywhere. The downside is too, once those 26 states are out of commission, to get generation back on is a lot of work. It's very difficult to restart a system from what we call black start conditions. So can create some real challenges. So that's why we don't see it all that often. Last one, I think we talked mostly about this, which is differential protection. This shows differential bus protection. The sum of the 3 currents here, according to KCL, should be 0, right? If there's no fault, then I1 plus I2 plus I3 had better equal 0 or approximately equal to 0. And up until recently, this protection was limited to buses, right? Because everything is in close proximity Transformers, the same thing, although transformers, it was a little more difficult because you had phase shifts and different windings that would change ratio, but there were ways to manage that. And generators. So you would see differential protection utilizing those. Sometimes you see them for motors, some big motors, but typically you'd only see that. Now we're starting to see it with, like I said, transmission lines. So that's differential protection. You can also have a different type of protection, although far less common than what you see. So we can see under frequency. So if the frequency is too low, then that usually means on a system level, you actually start to shed load. This is what we call rolling brownouts or rolling blackouts, depending on the condition. You actually will dump load. So in California, a few years ago, they almost had to implement under frequency load shedding because the system was so heavily loaded. Again, that's a really bad thing, but all the utility systems have automatic under frequency load shedding schemes so that they don't have a cascading failure of their system. If your generators are running too fast, then you can get problems with over frequency, and that can cause a different set of issues. Under voltage is another problem, especially for loads, because if you're doing a constant kVA load, if your power demand is constant, but your voltage is 80%, 70%, then you have to increase your current by the, essentially the same proportion to provide the same amount of power. So under voltage can be an issue as well. But again, far less common. One of the best things of the relays is they help you identify where the fault is. And they have a sequence of events recorder, or sometimes you have a separate device, which is a digital fault recorder, monitoring voltages and currents. Also, it's monitoring inputs and outputs of the different relays as to what this happened here, what happened here. And you can actually rebuild the events to figure out what actually happened. So you can take all the data that's provided and you can go and troubleshoot, because troubleshooting these, again, is very, very difficult. Sometimes it's impossible to figure out what's going on. So every substation has some sort of sequence of event or digital fault recording to go ahead and do it. The only difference is sequence of events are usually built into the individual relays, and they have kind of limited storage capability, where DFR has a lot of storage capability and can contain a lot of information. But you don't see DFRs as much anymore. And here's my last slide, which is more recent technology, which is using either GPS or you actually have lines that you inject a certain frequency. And whenever we come to a fault, the line rings back and it'll tell you that location. That's called traveling wave. And Schweitzer has a relay that uses traveling wave that actually is for sale. I don't know how many, I've never seen it implemented, but that's like the next generation of very accurate fault detection. The GPS stuff is normally you use synchrophasers and you can use clocks, but I haven't seen a lot of time synchronization to go ahead and protect for tripping. You do see it, like I said, for time stamping information and for like differential circuits to make sure you've got the same currents at the same times. But the more accurate stuff is using traveling wave to go ahead and detect that there's a problem there. Questions on the basics of protection? Like I said, this is about a thimbles full of what you would normally cover from a system protection perspective. It really is a whole another world to really get into it. And it takes years to be able to be a fairly competent protection engineer. I can do protection. I used to be better at it. I haven't done as much of it recently, but there's huge demand for doing power system protection. So there's tremendous demand. There's way more people doing substation automation. I wish Noah was here because I could pick on him a little bit. But substation automation, it's like, how do we get devices to communicate? So there's a lot of different things you need to do. But doing protection system engineering, it's a lot of based on your understanding of how the system operates. And so there's a lot of judgment calls that you have to make, where when you do substation automation, it's more, here's the condition, here's the case, and then you kind of get what you get. So it challenges things differently. But no, they're both necessary. And if you can do both, you're really in demand. But I've never met a really good substation automation engineer who could also do really good protection because there's too much to know about each of them. So usually they're completely separate. And when I've set relays in the past, I'll take care of all the protection stuff. And then another engineer will set all the automation stuff. They'll just tell me what the settings need to be, and then I would configure it that way. But the settings for a relay today, you might have 4,000 or 5,000 settings in a relay. Back in the old electromechanical world, you'd have 2, maybe 3. So one relay today can replace 50 different relays from not that long ago. So that's why when you walk into old substations, like you went into Orrington, you'd see all these control panels with all these holes cut out and all these massive rooms with like 4 devices in them, because 4 devices could replace 200, 300, 400 different relays. And so big changes as a result of that. So a lot of exciting things again, but it's all based on old approaches to how to do things, because engineers in the utility world are afraid to make changes. It's really scary to try something new because you're getting blamed, responsible, whatever. So what do? You don't make any changes. So sometimes it's a bad thing, right? You don't try newer approaches. Sometimes you have to, but for the most part, we try to go with the old because it's worked, right? Anybody here remember a pretty wide power outage other than the one that happened in 2003? 20 plus years, and it's been pretty reliable. I mean, if you think about how the power system, how difficult, the challenging it is, it's all over the place in the worst environment. And how many problems do you see when you flip your light switch with the lights not go on? Pretty remarkable. How many times have you started up your cell phone and I'm getting no text messages? I'm not getting cell service. My family, one time, this was an AT&T thing about a year and a half ago. They were visiting my in-laws in Florida, and they were heading back to the airport, and my wife couldn't get GPS because AT&T had an outage. And instead of going to the airport in the south direction, she went north and realized it too late. So it cost me $2,000 to get back on a flight because she missed her flight. So I debated saying, you should drive home, where it's $2,000 is a lot of money, but it was a very brief instance of thinking that because that wouldn't have gone over too well. But, that just happened. And she's like, well, it happened. It was okay. And same thing with me. It wasn't her fault. It's unfortunate, but you couldn't sue AT&T. But if that happened, everybody was trying to get from point A to point B and there's no power, that's a huge problem. And even when there is no power, remember I talked about the hospital losing power and how much of a problem it is? It really isn't, because hospitals have all kinds of backup power. If you were to go by Northern Lights in Bangor, you'll see there's like a stack kind of behind the old part of the hospital. They have all kinds of backup generation there. They could probably run, well, not the entire hospital, but a big chunk of it for 4 or 5 days without any power. 911 systems. You call up 911, dead storm, you got no power in your house. You pick up, if anybody has a wireless or a hardwired phone, I don't know if anybody does, but you pick it up and it still goes to 911. Even your cell phones, you can pick up any phone, dial 911, as long as the towers are working, it'll patch through to 911. They have to have backup power available. So anything critical has to do it. And it's not like these are buying generators from Home Depot. These are big, expensive, well-maintained, usually under secure conditions. Because if you're a bad guy and you wanted to mess around with Bangor, what do? You go lock the power out to Bangor PD, which is where I think well, I don't know if it's there, but I would imagine the 911 system is near there. And if you take out their backup generator, people are calling and they have no way of getting through to public safety. So causes a lot of problems. But again, we're getting into the last couple of minutes here. It's just how important electricity is. Imagine not having power in your dorm or your apartment last night when it was it -10? How long would it take before, I don't know how many layers of clothes you'd have to stick on, but pretty soon you'd leave your place, right? Because it would be 10 degrees in your apartment, all the pipes would freeze. So it would cause a lot more issues than otherwise. So anyway, questions on protection. You're overly protected. Okay. Like I said, I've already got the final exam review posted for the Thursday class. We'll do that Thursday. And come with any questions. Make sure you look at your grade book. I've encouraged you over the semester to take a look at it. If there's anything missing, it's going to go a 0. So sometimes I put stuff in. So if I put a 60 instead of an 80 or something like that, you should confirm that I've got the grades in there properly because it can cause issues. And all the homeworks and labs have been graded and tests. So there shouldn't be anything that is missing.
The syllabus, I didn't see any like letter grades to number.
Nope, I don't specify that because it depends a little bit on the class average. But it's generally the typical, 70.
98.
No, I don't go that high. Usually it's 92 or 93 for an A, typically. All right. Have a great day, TV Land. We will see you all on Thursday. Take care, everyone.
Hey, Paul, I got one question.
Yes.
For the in the homework section, there's like a real world per unit homework and then a real world per unit homework one. Was one
Yeah,
of
one of those
those
is not valid. So,
okay? I'm just making sure.
yep.
Cool. Thank you. Have a good one.
Thanks, Alan. You too. Have a great day.